Hello everyone, welcome to my channel ECE Scholastic. I'm Jasmine. I welcome you all to the 12th session of Discrete Time Signal Processing under Unit 1 Discrete Fourier Transform. In the previous session, we have discussed a general algorithm of DIT as well as we have seen some problems under DIT. In today's session, we are going to derive the general algorithm of DIF. As you know, DIF is nothing but decimation in frequency domain. I'm going to give you 4 important points under this DIF. So here the decimation is completely in frequency domain, as we all know that. And the second point is the computational stages be of the form n is equal to 2 to the power m. If we consider the value of n as 8, then we will get 2 to the power 3. So the 3 represents the number of stages of computation. So here we can say it has 3 stages of computation. Okay. And the computation stages will be like 8 point, 4 point to 2 point. But in the case of DIT, it will be like 2 point, 4 point and 8 point. Okay, it is a straight reverse of that. The third point is about the input and output. So here the input will be of the normal order, that is x of 0, x of 1, x of 2, it goes like this. And the output will be of the bit reversed order, which means x of 0, x of 4, x of 2, x of 6, it goes like this. Okay, which is a straight opposite of DIT. And the last point is about the twiddle factor. Here we will add the twiddle factor at the output side of each stages. Okay, and the twiddle factor for each point stages will be as follows. That is, for 8 point, we have W8 power 0, W8 power 1, W8 power 2, W8 power 3 as the twiddle factors. And for 4 point, it is W4 power 0, W4 power 1. And for 2 point, it is W2 power 0. So this is a small introduction about decimation in frequency domain. Before going into the stages of computation algorithm, let me derive a general algorithm that supports the computational stages of the 8-point sequence algorithm. Okay. So in general algorithm, what I'm actually going to do is, with the help of this x of k function, that is DFT of x of n is nothing but x of k, right? So with the help of this x of k formula, I will be finding what will be the output of first stage of computation. Okay, and from the output of first stage of computation, I will be finding the second stage output. From the second stage output, I will be finding the third stage output. Okay, here one important point is, once I find the expression for x of k, I will split this into even and odd parts. Okay, and with the help of this even and odd parts, I will proceed the further steps of this algorithm. Understood? Now let's move into the topic. That is, our first point is, I am going to consider a DFT of sequence x of n for n point. Okay, we all know the formula, right? What is the formula? X of k is equal to summation n equal to 0 to n minus 1 x of n w n to the power nk, where the value of k is also from 0 to n minus 1. Understood? Now I am going to split the summation, that is split the limit into 2 limits. My main limit is from 0 to n minus 1. I am going to split this to n by 2 minus 1, that is 0 to n by 2 minus 1, and my next limit will be obviously n by 2, right? So n by 2 to n minus 1. So on splitting this summation, I will get the answer as summation n equal to 0 to n by 2 minus 1 x of n w n to the power nk plus summation n is equal to n by 2 to n minus 1 x of n w n to the power nk. Okay, in order to make the limits of the summation to be a equal 1, I am going to substitute or replace the value of small n as n plus n by 2. Okay, we know we have 2 limits here, correct? N is equal to n by 2 and n is equal to n minus 1. So if I apply the value of n as n by 2 in this expression, what happens? So my n value is n by 2 is equal to n plus n by 2, which implies n is equal to 0, correct? And also if I apply the value of n as n minus 1, what will happen? N minus 1 is equal to n plus n by 2, which implies n is equal to n by 2 minus 1, correct? So my limit will be from 0 to n by 2 minus 1. So this is equal to, that is x of k is equal to summation n equal to 0 to n by 2 minus 1 x of n w n to the power nk plus summation n equal to 0 to n by 2 minus 1 x of, instead of n I am going to apply n plus n by 2. N plus n by 2 w n to the power, so instead of n I am going to apply n plus n by 2 into k. Okay, so this can be modified as, that is w n to the power n plus n by 2k can be written as w n to the power nk multiplied by w n to the power n by 2k. Okay, but the value of w n to the power n by 2k is approximately equal to minus 1 the whole power k. So I am going to replace w n to the power n by 2k as minus 1 the power k. Correct. So this can be written as summation n equal to 0 to n by 2 minus 1 x of n w n to the power nk plus summation n equal to 0 to n by 2 minus 1 x of n plus n by 2. So instead of this I am going to apply minus 1 the whole power k, and the remaining factor is w n to the power nk. Understood. Now I am going to combine the summations. So the value will be n equal to 0 to n by 2 minus 1 x of n w n to the power nk plus minus 1 the whole power k x of n plus n by 2 into w n to the power nk. If I analyze this summation, I can see that w n power nk, w n power nk is a common factor, right? So I am going to take it outside. My answer will be summation n equal to 0 to n by 2 minus 1 x of n plus minus 1 the whole power k into x of n plus n by 2 multiplied by w n to the power nk. Okay, so I have told you we will be finding the expression of x of k. So we have found out what is the expression of x of k. Now we are going to split this into even and odd parts. For splitting x of k into even and odd part, I am going to consider the even part as x of 2k and the odd part as x of 2k plus 1. Okay, now I am going to rewrite this expression. So my actual expression is x of k is equal to summation n equal to 0 to n by 2 minus 1 x of n plus minus 1 the whole power k x of n plus n by 2 multiplied by w n to the power nk. Now I am going to find what is x of 2k and what is x of 2k plus 1. So my x of 2k will be equal to summation n equal to 0 to n by 2 minus 1 x of n plus minus 1 the whole power. Wherever there is k, I am going to substitute as 2k. X of n plus n by 2 multiplied by w n to the power n, and instead of k, I am going to represent as 2k. Okay. Now I can write this as, so minus 1 the whole power 2k is nothing but which is equal to 1. Correct? So I can write this summation as summation n equal to 0 to n by 2 minus 1 x of n plus x of n plus n by 2. Correct? X of n plus n by 2. This term is multiplied by w. I am going to write this as w n by 2 power nk. Both are equal. Okay, you can write either in this form or in this form. So this represents we have computed the 8-point sequence into a 4-point sequence, or in other words we can say an n-point sequence is computed or divided to n by 2-point sequence. Okay, so this is my expression for x of 2k. Here I am going to consider this expression as g1 of n. Okay, this expression is g1 of n. Now I am going to find what is x of 2k plus 1. So wherever there is k, I will just replace 2k plus 1. Correct. So my formula will be summation n equal to 0 to n by 2 minus 1 x of n plus, so it is minus 1 the power k. So I am replacing this as minus 1 the power 2k plus 1. Okay. Into x of n plus n by 2 multiplied by w n to the power n, instead of k I will be replacing as 2k plus 1. Okay. Now I can write this as summation n equal to 0 to n by 2 minus 1 x of n. So this forms a combination of odd power, right? 2k plus 1 means it is a odd value, correct? So odd value, if we are having an odd power of a minus value, we will get the minus answer, correct? So the answer will be minus of x of n plus n by 2, okay, multiplied by w n to the power 2 nk and w n to the power nk. So I can write this as summation n equal to 0 to n by 2 minus 1 x of n minus x of n plus n by 2 multiplied by w n to the power nk into w n by 2 power nk. Okay, so this is my expression for x of 2k plus 1. So here I can say this value as g2 of n. Okay, so as a whole I can write g1 of n is equal to x of n plus x of n plus n by 2 and g2 of n is x of n minus x of n plus n by 2. This term is multiplied by w n to the power n. Understood? With the help of this g1 of n and g2 of n, I can write x of 2k as x of 2k is equal to summation n equal to 0 to n by 2 minus 1 g1 of n w n by 2 power nk. Similarly, x of 2k plus 1 is equal to summation n equal to 0 to n by 2 minus 1 g2 of n w n by 2 power nk. Understood? So this expression can also be equated to g1 of k and this as g2 of k. So this is the output of first stage computation. Now I am going to take this output as an input to second stage computation. Okay. So I got the value of g1 of k and g2 of k. So g1 of k is summation n equal to 0 to n by 2 minus 1 g1 of n w n by 2 power nk. Okay, and similarly my g2 of k is summation n equal to 0 to n by 2 minus 1 g2 of n w n by 2 power nk. Correct. Now I am going to split this summation. Split the summation means I am going to compute this for n by 4 point. Okay. So my answer will be g1 of k is equal to summation n equal to 0 to n by 4 minus 1 g1 of n w n by 2 power nk plus summation n equal to n by 4 to n by 2 minus 1, correct, g1 of n w n by 2 power nk. Going to replace n as n plus n by 4. Okay. So my answer will be summation n equal to 0 to n by 4 minus 1 g1 of n, okay, w n by 2 power nk plus summation n equal to 0 to n by 4 minus 1 g1 of n plus n by 4 into w n by 2 power n plus n by 4 into k. Okay. Now this expression will become summation n equal to 0 to n by 4 minus 1. I'm going to combine this g1 of n plus g1 of n plus n by 4. Okay. If I split this, what will be my answer? W n by 2 power nk multiplied by w n by 2 power n by 4k. Okay. So this w n by 2 power n by 4k, I'm going to write here w n by 2 power n by 4k. Okay, and the complete term is here also n by 2 nk and here also we are having n by 2 nk. I'm going to take this outside, n by 2 power nk. So this is my g1 of k expression. So what will be the expression for g2 of k? g2 of k will be equal to summation n equal to 0 to n by 4 minus 1 g2 of n plus g2 of n plus n by 4 w n by 2 power n by 4k the whole multiplied by Wn by 2 per k. The only variation is this is G1 and this is G2. Correct. If I'm going to split this G1 of k into even odd parts, I will get the answer as G1 of 2k is equal to summation n equal to 0 to, now my point sequence will change as to n minus 4 by minus 1, correct. So instead of this, I will be applying a value that is d11 of n into wn by 4 power nk. In a similar way, g1 of 2k plus 1 I can write as summation n equal to 0 to n by 4 minus 1 d12 of n w n by 4 per nk. Here also, G2 of 2k can be written as summation n equal to 0 to n by 4 minus 1 d21 of n w n by 4 per nk, and G2 of 2k plus 1 can be written as summation n equal to 0 to n by 4 minus 1 d22 of n w n by 4 per nk. Okay, now I need to find what is this d11 of n and what is this d12 of n, what is d21 of n and what is d22 of n, correct? So d11 of n is nothing but d11 of n is equal to g1 of n plus g1 of n plus n by 4. Okay, and d12 of n is equal to g1 of n minus g1 of n plus n by 4, the whole multiplied by w n by 2 power n. Okay, and what about this value d21 of n? d21 of n, instead of g1 I will write g2, correct? So d21 of n is equal to g2 of n plus g2 of n plus n by 4. Okay, and what is d22 of n? d22 of n is equal to g2 of n minus g2 of n plus n by 4. This term is multiplied by w n by 2 power n. What does this w n by 2 power n represents? It is the twiddle factor of second stage. That is, if we are considering the value of n as 8, n by 2 means it is 4, correct? So it is w 4 to the power n. So that is represented here. Understood? I can equate this expression to be d11 of k and this to be d12 of k and this to be d21 of k and this to be d22 of k, which is the output of the third stage. So that's all about the general introduction. Now let's move on to the complete DIF process. As I told you, we are considering here the value of n as 8. 8 means 2 to the power 3. We have 3 stages of computation, right? The first stage will be an 8-point sequence, the second stage will be a 4-point sequence, and the third stage will be a 4 sets of 2-point sequence. Correct. And the twiddle factors will be added at the output of each stages. Okay. And one more point is here, the input is in normal order, output is in bit reversed order. Okay. And we have found out what are the outputs at each stages of this DIF process. So initially, I am going to consider the 8-point DFT or n-point DFT. The input to this point is a normal order. So I am considering as x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. And at the output of this stage, I will be adding the twiddle factors, which is wn power 0, wn power 1, wn power 2, wn power 3. As we know, the output of the first stage is g1 of 0, g1 of 1, g1 of 2 and g2 of 3. Similarly, g2 of 0, g2 of 1, g2 of 2 and g2 of 3. Okay. And this is given as an input to the second stage. Second stage is nothing but 2 sets of 4-point sequences. And the output of this stage, we will be adding the twiddle factors, that is wn by 2 power 0 and wn by 2 power 1. The output of the stages will be d11 of 0, d11 of 1, d12 of 0, d12 of 1, d21 of 0, d21 of 1 and d22 of 0 and d22 of 1. Okay. And this will be given as an input to the third stage. Third stage is nothing but 4 sets of 2-point sequences, correct? So the output side, we will be adding the twiddle factor, which is wn by 4 power 0, and we will get the output in bit reversed order for DIF, correct? So the bit reversed order is x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. So this is the complete process. Now we are going to derive the expressions for each stages of computation. Let's start with the first stage computation. For the first stage computation, the input is x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. The output is g1 of 0, g1 of 1, g1 of 2, g1 of 3, g2 of 0, g2 of 1, g2 of 2 and g2 of 3. So how we are going to find the expression? We know the relation between g1 of n and x. From this we could say that the value of n is 0, 1, 2, 3. Correct. For G2 also the value of n is 0, 1, 2, 3. So as a whole we can say the value of n is 0, 1, 2, 3. And we know the expression for G1 of n. G1 of n is nothing but x of n plus x of n plus n by 2. Correct. Here the value of n is 0, 1, 2 and 3. Now I am going to apply the value of n as 0. I will get g of 0 is equal to x of 0 plus x of 4. If I apply the value of n as 1, I will get g1 of 1 is equal to x of 1 plus x of 5. If I apply the value of n as 2, I will get g1 of 2 is equal to x of 2 plus x of 6. If I apply the value of n as 3, I will get g1 of 3 is equal to x of 3 plus x of 7. Okay. Now I am going to write the expression for g2 of n. So for g2 of n, what is my expression? X of n minus x of n plus n by 2, which is multiplied by w n to the power n. Okay. Now I am going to apply the values of n as 0, 1, 2 and 3. On applying n as 0, I will get g2 of 0 is equal to x of 0 minus x of 4 multiplied by w n to the power 0. If I apply n as 1, I will get g2 of 1 is equal to x of 1 minus x of 5 multiplied by w n to the power 1. If I apply n as 2, g2 of 2 is equal to x of 2 minus x of 6, which is multiplied by w n to the power 2. If I apply n as 3, I will get g2 of 3 is equal to x of 3 minus x of 7, which is multiplied by w n to the power 3. So this is the expressions for first stage of computation. Now let's move on to the second stage computation. So in second stage computation, we know the input is g1 of 0, g1 of 1, g1 of 2, g1 of 3, g2 of 0, g2 of 1, g2 of 2 and g2 of 3. The outputs are d11 of 0, d11 of 1, d12 of 0, d12 of 1, d21 of 0, d21 of 1, d22 of 0, d22 of 1. So here as a whole we can say the value of n is 0 and 1. Now I need to write the expression that connects this g and d. Correct. So I know the expression for d11 of n is g1 of n plus g1 of n plus n by 4. We have derived from the basic derivation. Correct. So here the value of n is equal to 0 and 1. How can I find? I am going to apply the value of n as 0. So I will get d11 of 0 is equal to g1 of 0 plus g1 of 2. In a similar way, n is equal to 1 implies d11 of 1 is equal to g1 of 1 plus g1 of 3. Okay. Now I am going to find the expression for d12 of n. So d12 of n, the expression is the same but the opposite. Equal and opposite, right? g1 of n minus g1 of n plus n by 4, which is multiplied by a twiddle factor w n by 2 power n. Here the value of n is 0 and 1. Now I am going to apply the value of n as 0. I will get d12 of 0 is equal to g1 of 0 minus g1 of 2, which is multiplied by w4 to the power 0. And if I apply n as 1, d12 of 1 is equal to g1 of 1 minus g1 of 3, which is multiplied by w4 to the power 1. Now I am going to write the expression for d21 of n, which is equal to g2 of n. So here it is 1. Now I am going to replace it as 2. So g2 of n plus g2 of n plus n by 4, where the value of n is 0 and 1. I'm going to apply n as 0. I will get d21 of 0 is equal to g2 of 0 plus g2 of 2. Similarly, n is equal to 1. I will get d21 of 1 is equal to g2 of 1 plus g2 of 3. Now I am going to find the expression for d22 of n. So d22 of n, my expression will be opposite to this expression, right? So that is g2 of n minus g2 of n plus n by 4 multiplied by the Twiddle factor wn by 2 power n, where the value of n is 0 and 1. I am going to apply n as 0. I will get d22 of 0 is g2 of 0 minus g2 of 2 multiplied by w4 to the power 0, and if I apply n as 1, d22 of 1 is equal to g2 of 1 minus g2 of 3 multiplied by w4 to the power 1. Okay, so this is the expressions for the second stage computation. Now let's move on to the third stage computation. So here we know the input to this stage is d11 of 0, d11 of 1, d12 of 0, d12 of 1, d21 of 0, d21 of 1, d22 of 0, d22 of 1. And the output is a bit reversed order, that is x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. This can also be equated to d11 of k. This as d12 of k. And this as d21 of k, and this as d22 of k. Now I am going to find the expression that connects this d11 of, here it is d11 of n, okay. So d11 of n, d12 of n, d21 of n, d22 of n, and d11 of k, d12 of k, d21 of k, d22 of k. So from this we could understand the value of n is 0, 1 and also the value of k is 0, 1. Okay. I am going to write the expression that connects these two. So my expression is d11 of k is equal to summation n equal to 0, 1 d11 of n w2 to the power kn, or in other words we can say n by 4 to the power kn. Okay, where the value of k is also 0, 1. Now I am going to apply the value of k as 0 to this expression. I will get d11 of 0 is equal to summation n equal to 0, 1 d11 of n, where the value of k is 0, so this complete term will become 0. So on expanding this I will get d11 of 0 plus d11 of 1. Correct. Now I am going to apply the value of k as 1, so I will get d11 of k is d11 of 1 is equal to summation n equal to 0, 1. If I apply the value of k as 1, what will be my answer? My answer will be d11 of n w n by 4 power n. Okay, so this is equal to d11 of 0 plus d11 of 1 w n by 4 power 1. Or in other words, this can be written as d11 of 0 minus d11 of 1 the whole multiplied by w2 to the power 0. So this is the whole multiplied by. Okay. Now I am going to write the expression for d12 of k, which is equal to summation n equal to 0, 1 d12 of n w n by 4 power nk. Okay, if I apply the value of k as 0, I will get d12 of 0 is equal to d12 of 0 plus d12 of 1. If I apply the value of k as 1, I will get d12 of 1 is equal to d12 of 0 minus d12 of 1, which is multiplied by w2 to the power 0. Okay. Now I am going to find for d21 of k. My expression is summation n equal to 0, 1 d21 of n w n by 4 power nk. If I apply the value of k as 0, I will get d21 of 0 is equal to d21 of 0 plus d21 of 1. If I apply the value of k as 1, I will get d21 of 1 is equal to d21 of 0 minus d21 of 1, which is multiplied by w2 to the power 0. Okay, now I am going to find the last expression, that is d22 of k, which is equal to summation n equal to 0 comma 1 d22 of n w n by 4 power nk. So if I apply the value of k as 0, I will get d22 of 0 is equal to d22 of 0 plus d22 of 1. If I apply the value of k as 1, I will get d22 of 1 is equal to d22 of 0 minus d22 of 1, which is multiplied by w2 to the power 0. So this is the expression for third stage computation using DIF algorithm. Okay, as a whole, I can show you the butterfly structure as this. So here I have denoted the inputs, and here I have denoted the outputs. So as we have found the expression of the output in third stage computation, the d is a function of the output, therefore I have just represented as d11 of k, d12 of k, d21 of k and d22 of k here. But here I have replaced this as x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. Okay. So it is clearly mentioned that the Tudel factors are added at the output of each stages. So this is at the first stage output, this is the second stage output, and this is the third stage output. Okay. If a question is asked to derive the general algorithm for DIF, you need to write till this final butterfly structure. Okay. Hope you all understood today's algorithm. This is a bit complex when compared to that of the DIT algorithm, but it is very easy, I think. I hope you all enjoyed the session. Thank you for your patience. Thank you. Have a great day.